Okay, so if you hear me, then I think I should start. So I prepared a little bit of workspace for a short demo, um, which I think will take maybe half an hour or so. And after that, I suggest that we discuss in the chat, either by text or audio. If you have questions, you can ask them directly, but we need to take care that there is a delay of 20 seconds between the video and the chat, which makes it a bit difficult. And I have only one screen, so I will mostly look at the Pharo image and not at the chat. So I might not see, but Norbert will see them. Will see actually the questions and can actually tell me when there is one. There is echo. So there's echo because this room is has a bit echo, or maybe no. So everyone has to turn off the microphone but me. That's important. But I think that's the case. At least I don't see. And I'm using a headset, so that should not be a problem. At least let's check what is. So it should normally work. Okay, so what I want to show today is the current state of the improved reflection features that we have in Pharo 6. This is not too much different to the other presentations that I gave, for example, at Pharo Days. Partly because if someone is new to this, we need to start at the beginning. Else there is not, it's a bit hard to understand. So in Smalltalk, we have, of course, first-class methods. So that means every method is an object. So, for example, object halt. We can easily inspect it, and we see that's an object. Very nice. But the AST is only there if you ask the compiler for it. So to make it easy, there is a method AST on compiled method, and if you call that, you get the AST. With the new inspector, we have a nice tree view for this, which shows you only the nodes, so that you can quickly navigate in the structure, which is very beautiful. And there is even the possibility of selecting in the second pane the source code. And then while you are navigating to the AST, it will highlight exactly the part in the source code that you're looking at, which is very nice to understand where you are. And you can always switch to the raw view to see that this is a message node with all the state inside. So this is nothing new. There was always an AST in Smalltalk that you could ask the compiler for. What we did is that we changed it to be the refactoring browser AST, so it's very high level and shared across everything. And we have a nice helper method that gives you the AST. What this has in addition is that if you ask for it once, it is cached as long as the image is running. And so if you ask a second time, you will get the same object. So if I ask 2 times the halt method for its AST, it will return the same object, identical one. This is quite nice because this means that you can, for example, annotate the AST as you will see later. What you need to take care is that this is right now relatively simple, so that means it's a cache which is alive as long as the image is alive, and when you quit the image, it's cleaned up. So that means everyone who is using ASTs and has the need that they survive image restart, then the tool that does that needs to deal with keeping the AST alive over image restart, which the tools that I will show later actually do. And of course, from a memory perspective, it means that in the worst case, you will request the AST for every method, and then you will have the whole image as an AST, which will right now allocate around the same amount of memory like a freshly started Eclipse. So around 90 or 120 megabyte or something like that. Which can be a problem, but in normal uses that doesn't happen. So normally you're using this for debugging or for special tools, and you're only looking at parts of the system, so you will never even realize that it allocates memory. But we need to see what we will do with this in the future if that turns out to be a problem. But for now, it works very well. So after we have this, we have a way of getting from the source code to the AST programmatically. For example, I have here the demo. Let's check if everything is good. Yes. So we have here that you can ask any block for the AST node, and it will return you the AST, so and then you can inspect it. And this is, of course, the node from the AST of the whole method. So if you do that for a method that's in the system, this is a subtree of the one AST. The same you can do for contexts. For any context, you can ask for the source node. In detail, right now in Pharo 6 is actually that if you're down in the stack, you actually need to ask for source node executed, which gives you the node that if you're down in the deep in the stack that was executed to create this context. We are planning of cleaning that up and making it a bit simpler in the future. So for now, so for simplicity, you just need to remember source code. And there is a way to ask for, if you have a PC, so a program counter of your method, you can ask the method, give me the AST node of that PC. So for example, if you look at HALT, and you look at this as, oh, this is already a bit special, let's say. So if you look at the compat method of HALT, then you see that it actually has, that its bytecode has starts at a certain offset in the method. So for example, you have 22, 23, 24. And if you want to know which AST node compiled the bytecode at a certain PC, you can actually ask the method for this by just asking source node for PC, and it will answer you the corresponding AST node. So that's a bit what we have, so that you can actually not only introspect compiled methods, but you can get the AST of every method and look at it. That's very nice. When it gets actually interesting is that you can actually annotate any AST node. So if you look at the RB program node class, then it has in one of those categories, let's check, it's a bit in this browser a bit hard to find, here, properties, so we can lower it down to this. So it has a property API. Any program node of the AST can have a property. You can check if it's there, you can return the value, you can return the value, and if it's not there, do something, or you can set it or remove the property. Very easy. And the nice thing is that yeah, it even doesn't take any space if there are no properties, so only when you have a property it will allocate a dictionary for this property. So it doesn't cost anything as long as not used. Compiled method AST gives reflective method. No, so what the reason why it gives in my image reflective method is that I was preparing my image, and the demo that I will show some lines later that you see in the playground with morph, I did that with object. And after that, so I will explain when you see reflective method. So normally it should give you a compiled method. Only if you do something special, it's a reflective method. Yeah, it should be a. So what I was inspecting actually at some point was actually the HALT. So I wasn't asking for AST. So if you say AST, it will give you an AST node. So that means it's always the RB method node. But what I was doing is I was looking at the method itself, which should return your compiled method, which I wanted. But as I played with this image already, it actually returns me something else, and why I will explain later. But before, I wanted to discuss annotations. So because we can annotate any AST node, we can actually do crazy stuff with this. So one example is that in Pharo 6, the halt once and halt on count is actually implemented using annotations on AST nodes. It used to be that it was implemented with just global state. So there was one global halt once state in the halt class, and that's it. And now it's actually per call of halt once in the AST. And how this is implemented, I can show you quite easily. So if we look at in halt on the class side, we have once, which is the complete implementation of how it works. And this has at the beginning a bit of boilerplate code. So the first thing is that we have this debugger complete to sender pragma, which the debugger uses so that you do not see when you have the halt once in your code, so that you don't see the implementation of this machinery, but you see the first method where you actually put your halt. So this is internally used to skip some frames in the debugger when it shows up. Then we have something that if you do not have all this machinery installed, so if you have a minimal image, that it still works somewhat. So what it does, it is falls back to the standard halt. It could fall back on the old implementation, but I'm not sure if that makes any sense, but it would be possible. Yeah, then this is something to find the calling context. And then the real, actually the code that is interesting for us. So we have a recursion stopper that we need so that we do not run into a recursion if you put this halt in certain places in the image. But the most important, the real implementation is actually this, which I highlight, which is that we ask for which node did actually, so which is the AST node that called this self-halt. So the self-halt once. And if this we find with this, so we take the calling context and the source node executed, and we get the message node self-halt once in the code where I have written it. And then what we do is we use the property features of the AST. So we first check if it has already the property once, and we know that we should do nothing because we were already once here. So we just say return self. And then we put the property to true. And after we do the halt, the standard halt, so that we pop up the debugger. So that means the first time it will execute this code, it will put the halt once property and open the debugger, and the second time it will just do nothing. And it uses all this feature of having an AST available, having the possibility of getting from a context in the stack the message sent that actually created this context, and the possibility of reasoning about properties of AST nodes. Quite nice. The only negative side of it is, of course, that has property output. All this uses, for example, methods in dictionary. So if you want to put halt once in a dictionary method that is used here, one needs to take care. And for that, we have the recursion stopper. So that means that if you do that in code where that is actually executed while running this recursion stopper will make sense. Make sure that this is not a problem. But of course, it means that if you do it in recursion stopper itself, there might be a problem. But for most parts, it works fine. The same we do with the halt on count that we have in the image. This one is now implemented the same way. So that means that we have that we get the calling context, then we use source.execute to get the node, and then we check if there are any properties on it. And the property here is actually the count itself, which is very nice. And what this allows us to do too is to reason about it in the user interface. So let's see if this actually works. So if we take our nice test method, which still has a counter defined, which we need to remove. So imagine we would put a self halt on count here, halt on count 2. Then with a small refresh problem, we do have actually now a user interface that shows us the count number. So if at the beginning it's 0, and if we now would execute this method once and we mouse over, then it should normally be 1. It's not. Why? I have no idea. Let's see if it at least. No. Yeah. Some strange side effect, but it worked in that sense. So now it's 2, and it says click to reset, and then I can reset it, and it will again work once. Now it works 1, 2, click to reset. So that means we now have a per halt on count line of code state of the halt on count. And we even can make a user interface for it, which is very, very nice. So this already shows that you can do stuff with this functionality, but of course we can do more. So there is one one feature that we added to Pharo 6, and there were already parts in Pharo 5, I guess, is that what you would like to do is that you would like to be able to change behavior depending on annotations that you set on the AST. If you want to do that, you need to have a way of, when I set the annotation, the next call to that method should actually take into account that annotation, however you define it. So that means you need, or one way of doing it is that you need this kind of mini just-in-time compiler in the image, which allows you to tell the system before the next call of this method, please regenerate the bytecode. And this is actually integrated in the system by a so-called compiled method twin. And here, as an example, let's see if this is in a good state. So if we ask morph methods, yes, all the methods in morph are standard compiled methods. So we have here a list. So we can inspect, you see it's bytecode, nothing special. What we can now do with all these methods is we can say, please prepare to have a so-called reflective method for each of those compiled methods. Reflective method is just a wrapper around the AST, which has the same API-like compiled method, and which has a run within method defined, which actually executes the code. So if we do that, we can say create twin for all those methods. And if we now say invalidate, it will actually switch around the twin. So now we have a compiled method installed in the method dictionary and a twin, which is the AST, hold on by the reflective method. And if we say invalidate, it will actually install the reflective method in the system. And the reflective method knows its compiled method. So if we do that, then if we look at the methods of morph after that, then you will see that some of them now have, in the printout, they have reflective method behind, which means that they are instances of reflective method. And some actually are standard compiled methods. Right now they're printed with just the name. I need to think about better printout for these things. And they are standard compiled methods. And what this means is, as invalidate put the reflective method in there for everyone, this means that our kind of in-image just-in-time compiler already was active. So after we set invalidate to the method, the system actually tried to execute this method, for example, process event using or age resizing, because it's actually an active method in the morphic system. So what happens in that case is, if you look at reflective method, where do we have a browser? Then a reflective method implements a method called run within, and this is an interesting method. So if you install an object as a compiled method in the method dictionary, then the virtual machine will check if this is really a compiled method. If it's a compiled method, it knows what to do. It will just execute the bytecode. If it's not a compiled method, it will, instead of raising an error or crashing, it will actually call a method on this object. And this is this method run within. So it will say run with the current selector, with all the arguments in an array, and in a receiver. And that means we have all the information now locally in this method that we need to actually execute the method. And what our nice reflective method does is that it first makes sure that there is a compiled method installed, in case this happens in the compiler, so that we can actually execute this method immediately after this line of code. And then what it does is it compiles the method new, so it just calls the compiler, and it installs the compiled method of the newly compiled method over the original one. And after that, it will execute this compiled method using run within, but with a special method because of to avoid strange loops, which is always a huge problem with these things. Is, can I invalidate the whole image? Yes or no? And to be sure, there are a lot of tricks involved to be able to do that. So for example, this method is listed as a special method in, I don't know, no, they're not, I don't know. So some of the methods are listed somewhere, so when you actually, they are specially treated that they are always generated and not delayed, and others are skipped and all these things, to make sure that we can do invalidate the whole image and it doesn't crash. But that's not really relevant for the demo. So that means we can do this, and after you have created the twin, you can invalidate a method, and the next call will regenerate code. And that means that this is already enough to do interesting things. So you could take the compiler plugin architecture that we have and now write your own special plugin that on this recompilation will take into account your pragma or your property that you set on the AST. That would be perfectly possible, and I'm sure that there are use cases for that. Should not be too hard. So we have an example of a compiler plugin, but it's a bit simplistic. So this one just blankly replaces all 42 integers with a meaning of life. So it's not related to annotations. It's just to show that you can use a plugin to transform methods. But it would be perfectly possible to add a plugin that looks at your AST, and if there is a certain property set, it would transform the AST. What we added by default is one special kind of this plugin. So this is integrated by default, which takes into account a special kind of annotation, which is a so-called metalink. And I want to show a bit of demo of what that means and what you can do with this. For the demo, I will use a small special morph, so let's instantiate it. And open it, so it's just a morph. And as one can see, it actually fades to be invisible. And it has a method defined on it. If you call it, it will actually set it to red, and then it fades automatically to be transparent again. So it's very nice for visualizing execution, because it means that if you call it often, so if I call it very often, it will be kind of red, and if you call it once, you'll nevertheless see that it has been called, even so your call happened in a short time. And this is a very nice meta object for our system to play around. How can you activate compiler plugins? So right now, actually, I can show you. They are not active by default. What you have to do either in your class or globally is to add the plugin to the compiler. So as you can see here, we have for this meaning of life plugin, we have a special class which is AST transform example plugin active, which has on the instance side, it has a very simple example. It returns 42. On the class side, it overrides compiler. So the compiler so in Smalltalk it used to be compiler class. So you can override compiler class still in Pharo 2. But what we found out is that it's much better if you can actually, if you have an instance that you override for the compiler for your class, because it means that I can configure that instance to be to do certain things differently. And one thing that you can do, so one API that our compiler has, is that you can say add plugin, and you can add as many plugins as you want, and they are all called in order of adding them. So the first one will be called first, and they are all called in between. So we have a very nice comment even in the, we have not many comments, but this one is very nice. It shows you how it works. So there is the source code, then the scanner parser, then we have the AST out of that, and then we have a semantic checker, and here is where the plugin is actually called, or all the plugins. It's between semantic analysis and the AST translator that generates bytecode. If you want to enable a compiler plugin in the whole system, then you need to do it on the where compiler is originally defined. So if you check compiler, the implementation of it is in T behavior here, and there you can, if you change that, you change the compiler for the whole system. But the compiler plugin meaning of life demo is actually kind of fun. So if we look at this bytecode of this method, it should actually, and we have toggle bytecode, it should actually show you that it was actually, as the plugin is active, it actually does not return 42, but meaning of life, because it is transformed. Yeah, and these are plugins. So now with our morph that shows us can visualize execution nicely, we can demo the metalink system. So metalinks are special annotations on the AST, which kind of are from the domain of metaprogramming. So the idea is that a metalink binds the base level of your program with the meta object. And that means what you need for metalink is it needs a meta object as a target. So this is the object that you want to call something on. Then you need a selector of what you want to do with that meta object. And in addition, there are three kinds of controls. So the question is, should this link be, the call happen before the AST node that you put this link on, instead, or after? And we do it before, which is the default, so you could actually skip this. And what we do is we want to call node executed on our morph instance that we instantiated above. And so we can create this metalink object. And this one is now a special annotation on the AST. We have a nice API for that. So if you look at every program node, which does a lot of stuff, because what it does is it sets this link as an annotation, and it makes sure that the compiled method actually is that it is in the right state, so that the twin is created if it doesn't exist, that it's invalidated after setting the link. So if we do this on this method, it should actually mean that if we execute this, it should actually get read above, and it does. So if we look at this method, it's a very simple method. It just has an instance variable I, and it increments it by 1, and then returns it. So very simple method. Yeah, and this method now, every time it's executed, it actually does the call to the meta object. And around beginning, inner, and after, yes, exactly. Only that we don't have it on methods, we have it on any AST node. So I install it on the whole method, so on the every method node, which is a bit the same like a how were they called, a method wrapper. Method wrapper allow you to execute something before and after. But we can do it on any AST node and even on other structural elements, as I will show later. So this is nice. What of course is always now interesting is how does the bytecode look like. So if you now look at the bytecode of this method, then you see that it actually has added these 3 bytecodes at the beginning. So it uses to hook in to reference the meta object. What it does, it abuses our functionality of globals. So it actually compiles a local global binding, which is not a global, but which which is an association of name to object, which references the meta object. This way, yeah, this is how very nice how to do this. It used to use functionality of abusing the literal frame, but that's not really good because the literal frame might be read-only in the future, so this is much cleaner. And then it just does send node executed and pops the stack so that it's clean. And it shows that actually the code is very efficient. So it's really literally however we can reference this meta object and then do a send to this. So the performance impact is that you only pay for what you're doing. So in this case, you just add a message sent to the method. It's like always, if you do this for every message sent, if you do something on every message sent, then everything gets slower, clearly. But you only pay for what you are using, nothing more. Yeah, and then as we still have the link reference, we can say link uninstall, and if we now look at this one, then it actually is gone because link uninstall actually even removes the twin. So very very nice. Yes, with great power. It's actually meta. Everything meta is something that is designed to shoot in your foot. That's the idea, and it gives you a lot of power. But in a way, you should never use that in a normal program. So it's tooling to build frameworks, and not something you should use in your program itself. Yeah. So I said we have before, after install. The normal use is mostly you use before. Sometimes after is interesting, especially if you're interested in values of assignments. Then of course before you know nothing, after you know. Instead is very simplistic right now. So right now you can literally do one instead. So if you have an AST node, you can replace it with something else, but only once. So the kind of the last instead wins. So what if you look at the craziness of AOP some years ago, they have something called around, and what we need to do at some point is to take instead and make it into an AOP style around. But it's a bit complicated, and the question is, do you really need it? So for our use case right now, the instead is fine. Because one of the things that I wanted to do with getting this stuff in the real release is to do everything use case driven. So we only implement where we need something, not because it would be nice or because it's needed from a theoretical point of view. Yeah. So no. So the funny thing is that the ASTs are cleaned on on shutdown, but we do have a mechanism which even changed how it worked to make sure that this does not disappear on. So metalinks, if you put a metalink on a method, it actually is not cleaned on shutdown. And how this works, I think we need to look at the AST cache. So the AST cache announces AST cache reset. So I can explain that later. So we have. So we on AST. So what we do is we actually remember. So every time we create the twin, we actually record this in the system announcer. So when the AST cache is resetted, we actually afterwards reinstall all those methods in. So it actually hooks into the reset mechanism and makes sure that it's not removed. So yeah, so how do you call the original method? So what we have right now is that we have so-called reifications. So if we go to reflectivity tests and looks at reifications, no. Yes, so what we have is we can, where is it? Whoa. Yeah, there are my reifications. So there is a number of stuff that you might be interested in on the meta level. So you can actually pass stuff to the meta level, and one of these is supposed to be, maybe I have not yet implemented it. Select or sender this context value variable. No, it's not yet there. So the idea is that there is an operation. Do I don't have it yet? I don't know. So normally the idea is that you can actually reify the original operation and pass it on to the meta level, and this operation encodes the original thing. But for in general for the instead, there is a lot of things that if you make it into a real around and you it actually should have a so-called proceed, which calls the outer methods, so the one that you replace. But this is not yet completely implemented. Another question. Would it make more sense to write a compiler plugin for message send logging? So it depends. So you can, yeah, it could be that it makes more sense to do to hook into that, but the machinery. So you need to anyway hook. So the idea is that the metalinks are relatively low level. So the idea is that there is a machinery. So if you say, okay, I want to be interested in something, then you need to have someone who installs those metalinks and who knows where they are supposed to install. And this part of your framework needs to hook into method compilation. So every time you accept, your system needs to put the links back where it's interested in them. That's the idea. A compiler plugin, I don't know. It would be called automatically on every compilation, but is it really better? I'm not sure. So the idea is that metalinks are really low level, and you need to have machinery on top that deals with when they should be put back. what else did I want to say? So we can put the meta links on compiled methods for one, so the whole method. Or you can put it on other AST nodes, which means it can be on a message send, or it can be on variable assignment, or on variable read. And the reifications that are defined in the system are, depending on where you put the link, allow you to push different kinds of information to the meta object as a parameter. So for example, if you have a variable, you might be so both in assignment or variable, literal variable, instance variable, you might be interested in the name of the variable. So that means you can actually request the name to be passed to the meta object. And how this is done, if we copy and paste this one, is that you can, of course, call a method here with as an argument, and then you can give an arguments array with, right now inside you have symbols that describe what you're interested in. So in this case, it would be name. And if you put this meta object, this meta link on a variable, it would actually, as a parameter, give the name of that variable to the meta object. And in the same way, there are different defined verifications for different nodes. So for example, for an assignment, you can ask for the new value after the assignment, or the old value. You can always ask for the object at runtime, so for the self. For a message sent, you can ask for the selector. You can always ask for the context to be passed. For a message sent, you can always ask for the sender. For variables, you can always ask for the value. So it's variable assignment message. Yeah, so it's the message, you can ask for value, which is the return value of that expression. And things like that. And how can we use this stuff in the UI? So what we have added now are first users of this low-level stuff that are actually usable from the IDE itself. So for example, imagine that you would be interested in, what did I want to show first? Execution count. So that means we can put here add counter, and now, as you can see, we have a counter here in the user interface. This counter is first 0, and if we now execute this code a bit more, why do we get 2? That's a bit odd. Oh. Then our counter will be 5 at this point, because we executed 5 times this method. And the execution counter, so the execution counter is actually quite a simple object, a subclass. It knows its count number, it knows its meta link that hooks it in the code, and it knows the node that it's installed on. And then it actually very simply, the meta link that it uses is just meta link new. Meta object is the object itself, selector is increased. Then we set the link on the node that we configured it to, and we are done. So the goal is tools. So you can do, for example, a tool like this is interesting, that you can build it in just a couple of lines of code. So the direct use case while it's in the image is tools. So the idea is that you can you can build tools for very easily that hook into methods in a deep way. The other use case is, of course, research. So reflectivity allows you to hook into things in the image very easily, which are very hard else. But this, of course, is a very specific idea. But the main idea is that you can build tools very easily. There might be in the future that people use it to build kind of frameworks. So you could think that maybe if you want to build some, I don't know, system that has special things happening that are not really Smalltalk semantic, then you could use this to build it. But we will see if that is something that people will do. So this is the counter, one simple example of this. Another one is that we can add a watch point. So now we have a watch point in this, and for the watch point that we have actually a value, we better assign this to, we make one instance and then we actually call this multiple times. So now if we call it once, then now normally the watch point should be on 1. No, because the watch point is on I, which was red, and it's at 0. If we call it the second time, we get 2, but the watch point value now is 1, because we always look at the old value. Call it the second time, it's 2. So that means you can very easily look into values and you can look into your system without having to add a transcript output or use the inspector. So object-centric debugger, yes. So one thing that we are working on right now is to add the concept of object-specific metalinks directly into reflectivity, which is not really complicated, but it needs a bit of machinery, because what it uses internally is then an anonymous subclass, so that it actually, this metalink is globally defined, but it's only active in one object. And after that, you have metalinks that are actually active for only one object. So you define a metalink and you say active for this object. And if you install it globally, it will only fire in this one object, or in the collection of objects that you define. And with that as a basis, we can very easily add object-centric debugging to the system. This will come. The implementation, thankfully, is not specific. So it actually is, the code is only called as soon as you use the API to add an object, to make it object-specific. So it might be even that we will add it to Pharo 6, because it's just that code if not called. But that's good. Any other questions? Yeah, breakpoints. So we have self-halt in our system, and even the complicated ones with halt once, halt on count, halt if, they are very nice. But sometimes one would like to have a real breakpoint. And with metalinks, we now implemented breakpoints, and that I think is kind of interesting, that we were able to add breakpoints into the system with just a couple of lines of code. So now we have, on this method, we have a breakpoint. And if we now execute this code, it will actually break. Sadly, we have not yet the visualization of the breakpoint in the debugger. That will come later. As this was a halt once breakpoint, it only break once. So where did I? And breakpoint is implemented the same way as where do we have? our link. Yeah, so for example, the once breakpoint, it gets a break one shot, which is just a normal break link with option one shot true, and break link makes it just a simple meta link with a meta object is break, selector is break, and we take the options that we have set in our system. So that means that you can implement breakpoints with not that much line of code, and that's kind of nice, I think. And they come with all the nice effects of breakpoints, that they are you don't have to remove the self-halt when you commit your code, and you can globally turn them off and all these things. Very nice. Another thing that you can do with this is code coverage tool. There is only a small demo of it right now, which shows that this works. So what we do here is we have a very simple method, return 2 plus 3, and what we do is we install a meta link on all of these nodes, which will just tag the AST itself with this has been executed. And if we run it, it will highlight this method depending on how. So as we now have kind of multiple, so we have on the 2 we have a meta link, and on the whole message sent we have a meta link. It will highlight it a bit with more with deeper color depending on how often there is an annotation on it, because there are many meta links installed on this thing. So this shows a bit that you can actually do very nice tooling with it. It needs a bit of work to make it more usable. For example, you don't want to install meta links on every method, on every node. Why have it on 2 and on 3 and on plus? That it's not really needed, so it needs to be improved a bit. But you can do nice coverage analysis using this in the future. Another thing that we added is meta links. Originally they are about the AST, but there are other structural things in the system too. So for example, imagine you have, if you write object somewhere, this is a reference to a global variable. Is there an object that represents that global variable? And actually there is. So in Smalltalk, originally there was an association, which is called the binding. And what we did is that we made this into a subclass of association called global variable. And this global variable is a meta object for, and then this one. It's not working. It was working when I tested it. So the idea is that you can. Huh? Huh? Oh. So not working now. I don't know why. But normally you can put a meta link on a global variable, and with this way hook into all. Let's say maybe it works now. No. And hook into all accesses of a global variable, which is very, very nice. This, of course, there is no use case for a normal program that you would want to write, but for experimentation, it is very interesting. No. And as the same thing, you can actually put meta links on instance variables. So that means if you want to, for example, have a counter on an instance variable, this will be possible with this tool. So for showing meta links in Nautilus, there is a plugin, or there is a setting for something. So we have in this, we have an icon styler for meta links, which is turned off normally. So that the idea is that meta links should be not visible normally. You should have a way of looking at them when you debug your tool, but normally they should not be shown. There is a tool right now hard coded. So if you put this to true, it will show you, I think, meta links. So if you now go to TT, and we add a watch point. So now it shows not only the watch point, but the meta link in addition. If we click on it, it inspects the meta link. But this is more like a debug feature. In the future, there will be something easier to get this. Yeah, it will be a setting. Because it's really important to know where meta links are if you use them. But the idea is that they are supposed to be machinery that you'll not care about even when you're doing development. But what you build with it, this one will have, of course, visualization in the method. Any other questions? Or do we switch to the tech talk on to the talk mode on the other chat? Or is this good enough? Huh? Ah, yeah. And it's already a bit late. So I guess that it is fine to answer a bit more questions here, and then we can wrap up. Properties on classes. Not. Actually, yes. Performance. So they actually only mean, so a meta link is in the end just a description of a message sent that you add before, after, or instead of something in the AST. Nothing else. So you will do that message send, which of course means if you do it for every message sent, you do another message sent, everything gets already by default slower. But it's only that. It's as if you would write that message sent in the method. Well, properties on classes. We do have already properties on classes. And it's actually already used for classes to be, so if you look at property, so tBehavior has already property add. And this means that you can put properties on any class. And it's used for if a class is no, how's it called? Obsolete or not. So is obsolete used to look at the name of the class, and if it started with an obsolete, the string, it was obsolete. And what we did, the problem was that it was actually a bit slow to check, because you always need to do a string comparison. And now it actually uses a property. So a class is obsolete if it has the obsolete property put to true. Instance side slots and class, why should they be unified? So you can make, of course, you can store a state in slots, which makes them into, so class variables, or so they are not really, in which sense, unified. So what we have is that if we turn on slots, that of course you have slots on the class side too. And even class variables are use the same mechanism. Class properties are not persistent with Monticello, so they are purely an implementation artifact. There's no syntax in the language for them, so they are not part of the class definition. This could be something in addition, but it's a bit like that you have properties on methods and pragmas. Pragmas are syntax, properties are that you can set. And the same here. So we have the property level, but not the pragma level. Yeah. So video. Yeah, I will turn off the video.